Hi everyone, my name is Timofey Bryksin. I'm going to talk today about one of our projects at JetBrains. It's about Kotlin and anomalies in Kotlin code. Very briefly, Kotlin is a general-purpose statically typed programming language that combines both object-oriented and functional programming features. Initially, it was designed to interoperate fully with Java and mainly target the JVM and Android platforms, but it also now can be compiled to JavaScript or native code via LLVM. Kotlin is a relatively young programming language and has an active and continuously growing community. For most people, Kotlin looks like a streamlined version of Java with its extension functions, properties, nullability support, coroutines, and other stuff. And as demonstrated on this slide, when people use these really cool features, their code generally becomes more clean and concise. But there are always people who just do things differently, not how they're supposed to be done. This is a piece of code from a compiler of the fourth programming language. Who knows why it was written, and technically it's written in Kotlin, although sometimes it does not look like it at all. We call such fragments anomalies, in a sense that they're written differently than the rest of the code in the community. This code could be syntactically correct, it could even work very well, but somehow it differs from the majority of the code written in this language. Such code examples are usually of great interest to language developers. First of all, they could reveal the previously unnoticed compiler defects, could be used for compiler performance or regression testing, and may even provide some hints on how to improve the language itself. So the informal task description that we got was take all the Kotlin code in the world and find some weird programs. There are several papers and tools trying to search for anomalies in programs. The first two mentioned here are based on static analysis. The first work uses graph-based anomaly detection methods to catch unusual method calls and other typical areas of the control flow graph. The somewhat similar idea is presented in the second paper. The authors propose mining usage models for all objects from the source code as sequences of their method calls and detect possible defects as abnormal usage patterns. The deduce tool induces invariant rules for the values of each expression in the program, so then anomalies in those values could be reported. The last paper here also uses dynamic analysis, but they collect and analyze traces of system calls. These last two approaches are based on running the code, which in our case does not seem feasible for a very large code base. Projects might have all kinds of weird dependencies, and who knows how they're supposed to be run. Also, all these approaches are helpful if one is trying to find logical errors or architectural issues in programs, and well, therefore they're targeting programming language users, not its developers. Okay, let's get back to the task at hand and see what we can do with it. First, we should determine what should be analyzed. Kotlin code exists in the form of a text or in some form of a syntax tree, and there are representations at different compilation stages, like the produced JVM bytecode, LLVM bitcode, and so on. Analyzing both these groups seems to be beneficial. Source code analysis gives us anomalies in the language use patterns, and intermediate representation analysis additionally provides data on compiler performance issues. And what's best, we can combine them. For example, find code fragments that are anomalous in bytecode and are not anomalous in the source code. Such cases clearly indicate some issues in the compiler or somewhere else. In data science, the anomaly detection task is a well-known problem. We could build vector representation for the input code and perform anomaly detection on this vectorized data. And when we get anomalies, we could somehow classify them according to the types and assess the result. This diagram shows the workflow, which is pretty straightforward. We get the code using GitHub API, we forked the compiler, and made it save all syntax trees that it builds. Based on these syntax trees, we calculate features, run algorithms, look at what we got, repeat. At some point, we collect the anomalies and show them to the Kotlin compiler team to see where to change our course. To get data, we fetched all GitHub repositories which stated Kotlin as their main language, were created before March 2018 and were not forks of some other repositories. In total, we got more than 930,000 source files. Speaking about bytecode, GitHub supports publication of the project's build packages, which allows the direct collection of bytecode. Even though the dataset we collect in this way is relatively small, that kind of extraction approach is highly convenient for us because it allows to collect the bytecode produced by its developers instead of figuring out the correct environment for each project and building them ourselves. We managed to obtain more than 41,000 compiled class files, which we then transformed into lists of JVM instructions. Building vector representations for code fragments is a hot research topic right now. Basically, all such approaches fall into two groups, explicit and implicit features. Both groups have their own pros and cons. Explicit features are very descriptive. Just look at their values and often you get a hypothesis why this particular code fragment is considered an anomaly. However, it is challenging to choose which set of features to use, since many of the metrics are based on opinions on what good and bad code is. They are complicated to use when we don't know what we're searching for. An alternative here is implicit features. They often lack expressiveness and are hard to interpret by humans, but they could capture code features that were not obvious beforehand. In the first experiment, we used straightforward explicit features. A vector of 51 software metrics was collected for each of the 4 million functions, and for them we ran a local outlier factor and isolation forest. We reduced the dimension down to 20, which left us with 0.8 variance explained, but much more friendly computation time. The contamination here defines the proportion of outliers in the dataset. Since we had no idea what to expect, we just set it to some small numbers like 100% to make the result observable by humans. As a result, we got 405 anomalies for each algorithm, which we manually looked through and left 322 in total, which from our point of view could be of interest to language developers. The second experiment on source code was based on implicit features. This time we used n-grams to form feature vectors, namely bigrams and trigrams. It resulted in a huge amount of different n-grams, which we filtered, throwing away rare and frequent n-grams since they contain less information for us. And then an autoencoder neural network was used to find outliers in this data. We had a very simple network architecture with only one hidden layer. We experimented with different compression rates of this middle layer, and this approach left us with a plausible result of 191 anomalies. Code anomalies could be evaluated in several ways. Performance tests seem like a good choice here. However, for syntax tree anomalies, we can only measure the performance of the compiler's parser, which is usually one of the simplest parts of a compiler. And performance problems usually arise during other compilation stages, such as type inference, resolving, or code generation. Also, there are other anomaly types, not only performance-related ones. For example, anomalies that highlight problems in the programming language design. Such problems can only be detected by an expert who deeply understands the concepts of the programming language and the internal structure of the compiler itself. So we have invited the development team of the Kotlin compiler to serve as experts in our study. 2 people agreed to volunteer. We asked them to evaluate each anomaly using a 5-point scale where 1 corresponds to mostly useless find, and 5 is a find that may greatly improve the language design or could be used as a compiler performance test. We also ask them to rank each of the anomaly types that we obtained on the post-processing step to assess the perceived importance of individual types. Anomalies from 10 types were marked as 4 and 5. They are shown in this table. Let's look at some examples of them. Here's the when statement with more than 120 case branches. I sincerely hope it was automatically generated. Here's a function with 22 type parameters. The compiler does a lot of work around generics. For example, in some complex cases, it could even reach exponential complexity while inferring types. And code examples like this are good performance tests. And this detected anomaly uncovered a bug in the parser. This syntactically incorrect code crashes the parser with a Stack Overflow error. And the last experiment I'm going to talk about today features both source and bytecode analysis. Here we also used this n-gram-based approach with an autoencoder network. We were searching for compiler-induced anomalies, called fragments that are not anomalies in the syntax tree form, but are anomalies in the bytecode and vice versa. This approach left us with 54 unique anomalies. Here are the results of the assessment by the same two experts. Bytecode anomalies correspond to the properties of the compiler rather than source code. It makes such anomalies difficult to classify, hence we did not assign class labels to them here. Some of them were pretty useful. Here's an example when a function of 10 lines of code is translated into a 4500 bytecode instructions. It's clearly a runtime performance issue of the framework they used. Someone created a large inline function, someone used it 9 times in a row, which resulted in a very inefficient code. A simple function code instead of inlining would be way more effective here. So, to sum up, the detected syntax tree anomalies were divided into 3 categories. First, anomalies that correspond to language design issues. Such anomalies were noted and archived by the Kotlin compiler team for further discussion and research. Second, anomalies that correspond to cases when some parts of the compiler might work incorrectly or slowly. And third, anomalies that correspond to potential performance issues of the program's runtime environment. The experts considered such anomalies as valuable compiler tests and accepted to include them in the compiler's testing infrastructure. The detected compiler-reduced anomalies were caused by the following issues. First, non-optimal code generation cases in the compiler that manifested in some rather exotic code examples. In such cases, the anomaly can be used as a test for bytecode generation. Second, rather complex functions were inlined in code fragments that were considered abnormal. Such cases have nothing to do with compiler problems, obviously, but could be very useful for developers of libraries and frameworks. And third, there were also several cases when some of the compiler optimizations worked really well, and complex syntax trees were minimized to form a rather simple bytecode. Such cases are not issues of any kind, but they can nevertheless be useful to compiler developers. For example, they can learn from the successful optimizations and further improve them. So, despite our pretty straightforward initial experiments, we already managed to get some useful results. Our code is open source and is on GitHub. Here's the QR code. If anyone's interested, feel free to drop us a message. That's it for my talk today. Thank you very much for listening.